Okay, great. Thanks very much. It's great to be here. I'm going to cover 2 advanced topics in predictive analytics. A couple slides about my work. As you just heard, I'm the founder of the Predictive Analytics World Conference Series. So this is the leading cross-vendor event focused on commercial deployment. Our main event is a umbrella business-focused event, but we also have industry vertical specific events that cover financial services, healthcare, manufacturing, and workforce applications. Our next event is in a couple weeks in Chicago, then October in New York. So you can check out the full agendas at predictiveanalyticsworld.com. And I'm also the author of this book. Got a couple copies with me. So the first couple people who grab me during break can take these copies. The subtitle of the book's actually an informal definition of the field. So it's Predictive Analytics, the power to predict who will click, buy, lie, or die. And this, just give you the elevator pitch for the book. As a former academic, this is a conceptually complete introduction that's used as a textbook at more than 35 universities, but doesn't read like a textbook. It's very much in kind of the pop science, anecdotally driven, kind of entertaining mode, accessible to any reader. Those of you who are obviously more experts will find treatment of advanced topics in the last 3 chapters. And then that's me in this analytics music video. Let me just explain this. This is actually the best ever educational predictive analytics rap music video ever created. So I strongly encourage you to check it out. 3.5 minutes long at predictthis.org. So Spark empowers predictive analytics and machine learning by extending the reach, the scope, the potential. But most of the core analytics concepts and challenges remain the same. So what I'm going to do is quickly define predictive analytics, and then I'm going to cover 2 advanced topics I want to make sure are on your radar. Uplift modeling, which is a way to optimize for persuasion, for example, in marketing applications. And ensuring sound science, averting a common pitfall, sometimes known as p-hacking, where you're fooled by randomness in data into drawing a false conclusion. That is that your predictive insight is BS. So predictive insights are key. You know, perhaps the most valuable deliverable we get from data are predictive insights, such as one credit card issuer discovered people who are observed spending at a bar are higher credit risk, more likely than average to miss repeated credit card bill payments. Whereas if you spend with your credit card to buy the little felt pads so you don't scratch the floor or the bottom of your chair, lower credit risk. People who like curly fries on Facebook are more intelligent. Neighborhoods of San Francisco exhibit higher rates of certain crime, also have a higher demand for Uber rides. So these types of insights are the building blocks. I call this the prediction effect, which is, for all intents and purposes, data is always predictive. We do the analysis. We get these insights that serve as building blocks, independent variables, essentially, for predictive models. So here's our more complete definition. Predictive analytics technology that learns from experience, by which I mean data. To predict the future behavior of individuals, everyone gets a predictive score. They output a predictive model that's a probability. As to the probability that individual will click, buy, lie, or die, like in the title of my book, or commit an act of fraud, any kind of outcome or behavior that may be valuable for your organization to predict in order to make decisions. It's actionable. To derive decisions such as whether to contact for marketing. Now, by predictive analytics, I'm essentially being synonymous with machine learning. And for many business applications, they're exactly synonymous. After all, they both refer to the same set of predictive modeling or machine learning methods that include decision trees, naive Bayes, neural networks, and ensemble models, right? Both these are included underneath the more umbrella terms big data and data science, which are subjective. I mean, let's do something smart with the data. Same thing for the older term data mining. So here's a quick back of the napkin arithmetic example, the value for targeting marketing, which will help me introduce the uplift modeling. So let's say we're doing mass marketing, these 2 million customers. to these 1 million customers, but it costs $2 to contact each one, so we're going to spend $2 million contacting everybody. If our response rate is 1%, we have 10,000 responses, which means we get $240 profit per response. We're going to have 2.2 million come in after spending 2 million. Bottom line profit is $200,000. How much better with a predictive model? Well, if we score all the individuals and rank them most likely to least likely to respond if contacted, right? And the predictive model has been doing a pretty good job in doing so. The top 25% may have a lift of 3 that is 3 times the average overall response rate if contacted, 3%. And if we use that 1 million yes/no decisions to decide which 25% to contact we're targeting, we eliminate 75% of the marketing cost. The bottom line profit skyrockets by a factor of 1.15 million, which you can determine with the same arithmetic I did a minute ago. Right, such a dramatic improvement just by more intelligently targeting that I actually paid my graphic designer, who I pay by the hour, to draw this star explosion thing. On the flip side, this isn't an accurate crystal ball-like model. I don't have high confidence if any one individual is definitely going to buy within that 3% group. So in that sense, this model totally stinks. But it's a skunk with bling, another alternative definition of the field because of the an unambiguous value. I call this the prediction effect. A little prediction goes a long way. Predicting better than guessing. Generally, more than sufficient to drive a great improvement to bottom line in rendering mass-scale operations more effective in marketing and beyond. And as such, all of these action verbs taken unto us, the way we're treated and served in modern-day society by financial institutions, government, law enforcement, healthcare, are more and more driven more optimally by way of predictive analytics. Right? This is one of the last remaining points of differentiation between yourself and your competitor. So they're very much jumping on the bandwagon, and millions of these decisions are driven by the output of a predictive model determining whom to call, mail, approve, test, diagnose, warn, investigate, incarcerate, set up on a date, or medicate. So I like to call this predictive analytics the latest the latest evolutionary step of the information age, where we've moved from applying engineering to determine how to warehouse, store, and manage bigger and bigger amounts of data, to the application of science, where we're learning from the contents of the data, what it tells us, what it means, how to make predictions in order to render all the main actions we do as organizations more effective. Kind of a big deal, probably a good idea we get it right. So let's move to the first of these 2 advanced topics, uplift modeling. A moment ago, I was patting myself on the back because I did such a great job targeting and cutting the costs of my marketing campaign by a total of 75% with relatively lower loss in the actual business I was getting. The thing is, am I missing a major question about how I could have cut the costs even further? An often overlooked question in marketing: who of these green respondents would have bought anyway if we didn't contact them? Let me turn them purple. Could be half of them. The product's flying off the shelf. These are so-called sure things customers. We didn't have to spend the $2 to contact them. They would have bought anyway. So it seems like there's something else we want to predict other than will they buy if contacted. It's will they buy if not contacted. It's like a double question. In fact, we're going to move with uplift modeling from the standard targeted prediction, that is the standard dependent variable, will the customer buy if contacted, and that's standard for targeting marketing response modeling. I'm going to change that just by adding one word to the sentence. Will the customer buy only if contacted? In other words, will the customer buy and not buy otherwise? In other words, is it a good idea to contact this customer? Would contacting them persuade them? Will it increase the chance that they're going to have the positive outcome? Same thing in healthcare. Will the patient become healthy only if treated? You take a pill, your headache goes away. But how do you know it wouldn't have gone away otherwise? So the type of predictive modeling methods that do this, the form of machine learning methods that do this, is called uplift modeling, which is analytically modeling to predict the influence on a customer's buying behavior that results from choosing this marketing treatment option over an alternative treatment. So instead of the standard prediction, which sort of seems obvious, what I want to predict is, the future, or the behavior, or the outcome. No, we're moving from that to predicting for each individual, how much more likely is this treatment to generate that desired outcome than an alternative treatment, or lack thereof, a passive treatment. And this very much applies in your own personal dating life, right? Because this is just a little dating coach thing for you. When you're in the restaurant, you're not there for the food. This is a sales call. You're both the director of marketing and the product, so it's very important you predict ahead of time which treatment's going to lead to a positive outcome with your prospect. So how many people saw this movie, Groundhog Day? Okay, most of you, like 84.3%. Bill Murray's stuck living the same day over and over again. He totally hates it. He's in his own personal hell until he recognizes that this supernatural scenario provides for him the unprecedented power to test different treatments on the same prospect under exactly the same circumstances and see which leads to a positive outcome. So let's watch a 40-second clip of the movie Groundhog Day.
You weren't in broadcasting and journalism?
Mm-mm. Believe it or not, I studied 19th century French poetry.
What a waste of time. I mean, for someone else, that would be an incredible waste of time. It's so bold of you to choose that. It's incredible. You must be a very, very strong person. Yeah? You weren't in broadcasting or journalism, anything like that?
Believe it or not, I studied 19th century French poetry.
La fille qui j'aimerais sera comme bon vin, que c'est bon fuira un peu chaque matin.
You speak French.
Oui.
Do not try that at home. The sad fact is you can't try it at home because in real life there's no do-overs. The only recourse is prediction. Now, what is Bill Murray trying to predict in this scene? Is he trying to predict whether she'll fall in love with him? No, that would be the outcome. He's trying to predict, will this treatment increase the chance of that positive outcome? And the only reason he's able to do it, by the way, and what you need for this class of predictive modeling methods is a control set. So you literally have a treatment control set, two training sets that look exactly the same as one another, and it's just a real paradigm shift because the machine learning method actually learns from both of them at the same time. It has to be considering them both together. That's very different than pretty much everything most senior practitioners in the field have seen for decades. But it works. US Bank did a head-to-head comparison targeting standard direct targeting of direct mail, selling a line of equity to existing customers, with response model, predicting who's going to buy if I contact them. They were hitting some sure things. They were also hitting some customers where they had the adverse and decreased the chance of them buying. They were going to buy, and now they weren't. And as a result, comparing that to the improved one of targeting with uplift modeling, increased return on investment of that marketing campaign by more than 5-fold. The same basic proposition applies to the other main marketing application of predictive analytics, which is targeting retention offers. With churn modeling, you're looking at this customer as a magazine subscriber. Should I expend the cost of contact and a discount in order to retain or attempt to retain this customer? What are the chances that tomorrow, if I do so, that they will no longer be a subscriber? The problem is that these retention offers have potential to backfire. Most famously, within telecommunications, you get a pamphlet that says, hey, you're going to get a free phone if you renew your contract, but now you've been reminded that your contract's going to expire. And you actually decide, oh, thanks for the reminder, I'm out of here, I've been wanting to defect. These are called sleeping dog customers. So you want to exercise the adage, let sleeping dogs lie. Don't trigger customers to leave who otherwise would stay. In fact, the Obama campaign 2012 found very much the same effect and also did apply uplift modeling. They were calling it persuasion modeling. If a campaign volunteer went to the door of certain voters, they actually decreased the chance of getting the vote, increasing the chance that person would vote for the opponent candidate, Romney. So a leading telecom big one in Europe, Telenor, did a similar thing, head-to-head comparison of standard best practice targeting a retention offer with a churn model, right? So that's just predicting the outcome or behavior, who's going to leave without contact. And compared that to uplift modeling, which is it a good idea to extend this retention offer? Am I going to decrease the chance that they'll stick around by doing so? And in that head-to-head comparison, saw a return on investment improvement of that retention campaign by a factor of 11. So now moving to the second of these two advanced topics I wanted to cram in here. So I've been talking about more optimally defining what the prediction objective is. But now let's just talk about whether the predictions are good in the first place. Here's a cautionary tale. Seattle Times ran an article that led with this example that came from a Kaggle competition. An orange used car is least likely to be a lemon, which is a bad used car that breaks down. So you're at the used car dealership. If you believe in this insight, buy a car that's this color, orange, because according to the data, 12% of cars in general are lemons, but only 8% of the orange ones turned out to be lemons. And this result by itself, according to a statistical test, was interpreted as being statistically significant because it had a p-value less than 1%, which basically means, just as a reminder, if this hypothesis is null, if it's a BS insight, if orange cars are no different than other colors, well, there's still some chance we'd see that result in the data anyway, or a result as compelling or as extreme, but less than a 1% chance. So that seems like pretty good evidence. However, this standard statistical test has been misapplied without taking into context what you get, which is that there's a lot of other hypotheses that have also been evaluated, especially in the era of big data. This is becoming a bigger issue. So having high confidence on something that you shouldn't have that high confidence is a big problem. As we all know, BS stands for bologna sandwich. It also stands for bad science. We need to make sure that we do not report results with confidence that it doesn't deserve. This is really bad. It's the fundamental question for machine learning. Has the machine learned something real? So talk about probability for a second to get a sense of how this comes up. Your friend calls and says, I just won the jackpot wheel that's a 1 in 100. It sounds pretty remarkable, so you might get excited on behalf of your friend, who then says, well, let me provide some more context. Actually, that was not the only time I spun the wheel. I spun it a number of times. You ask, did you spin it 20 times? No, I spun it 70 times. So now this thing that seems so remarkable, with a broader context, maybe is not so remarkable after all. If you spin the wheel once, you'll probably lose, 99% chance of losing. If you spin it 70 times in a row, for a series of 70 spins, the chances of losing every time are raising that to the 70th power, which is about 50-50. There's about a 50% chance you'll lose every time out of 70 spins, and about a 50% chance that you'll win at least once. And we're going to see the same thing with checking hypotheses. Scientific research are conducting the same probability game. So let's say you think you solved baldness and what appears to be statistically significant according to a t-test or some other hypothesis test. There's a significant increase in average hair growth rate with your magical treatment in comparison to a placebo. The problem is, if you tried a whole bunch of hypotheses that are all null and you cherry-picked it, like applying a banana topically, it's unlikely to solve baldness, although it might be worth trying, as would be this treatment of watching the Brady Bunch or touching Bruce Willis. You don't know until you actually do the experimentation, get the data, and do the analysis, right? There's a restraining order. So let's assume we have 70 hypotheses that are all null. They all fail, because that's not hard to imagine. It's a hard problem to solve. It turns out, by applying yourself to that risk of being fooled by randomness in the data repeatedly, under certain reasonably assumed conditions, it's exactly the same math, where there's about a 50% chance that they'll all be true negatives. You'll never be misled. It'll say no, 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 no 70 times, no cure for baldness. But there's a 50% chance that at least one of these data samples corresponding to one of the hypotheses you're evaluating will end up, just by random perturbations in the data, being something that in isolation is potentially compelling enough to mislead you. if you're not taking what's called the vastness of search into effect. So in a nutshell, if you spin the wheel enough times, eventually you'll get lucky. And if you test enough hypotheses, eventually you'll get unlucky in the sense that you'll come across that data sample that seems compelling enough to mislead in isolation. So this is called the vast search problem, because we're searching many different hypotheses, potentially cherry picking the best one, also known as p-hacking. So in this sense, bigger data is more hazardous in the sense that it's wider. There are more independent variables. You're checking each one. Even John Oliver at Last Week Tonight covered this topic. So you can adjust for it, and you can compute a p-hacking. You can compute a p-value based on certain simulation methods or arithmetic methods. So for example, when you just account for the vastness of searching all what were 14 or 15 colors in the database, the actually recomputed p-value was more like 7 to 9%, much too high to hang your hat on and report in a newspaper. That's very conservative because it doesn't take into account what was even much vaster search across hypotheses, make, year, model, all the different columns in this database of used cars. So what we need to do is hold ourselves up to that higher standard, evaluate for statistical significance in a way that takes that into account, but that means fewer of your hypotheses will pass that hurdle. So to accommodate for wider data, more independent variables, which means potentially more discoveries, but more risk of being misled, you want to compensate for that by making the data longer. More examples, more rows from which to learn. And if you have that, of course, you want to employ the best practice of having a held-aside test set. So you're going to train on this model and then evaluate on the held-aside set that serves as objective measure. Now, just one technical note before I wrap up. As you're doing this train test, which is an ad hoc manual standard process, you're doing it yourself, train test, what you're starting to do is bias that test set because you're effectively using it to select a hypothesis. So you've got that vastness of search. It's not used to generate hypotheses, but it's being used to test. So ideally, now you once again need to take into account that vastness, or most ideally have another held-aside validation set. So I'm going to close with a quote from Nerds on Wall Street, and then you'll get the PDF. It's got the notes section, a lot of additional citations and links, including 2 more slides that have specifically a bunch of references on those 2 topics. So David Lineweber said that an unlimited amount of computational resources is like dynamite. If used properly, it can move mountains. Used improperly, it can blow up your garage or your portfolio. Thanks for your time.